Hello, this is part 1 of lecture 2 of linear algebra, and this part is about linear subspaces and spanning sets. Before we define what linear subspaces and spanning sets are, let us define generalization of lines in the plane and planes in three-dimensional space. A hyperplane, by definition, is a subset of points in n-dimensional space that satisfy the following algebraic equation. Here, a1, a2, up to an and b are some fixed real numbers, such that at least one number among a1, a2, an is not zero. Some of them can be zero, but not all of them. Because if all of them are zero, we get very strange equation that looks like 0 equal to 0 or 0 equal to 1, which do not define as what we call a hyperplane. If hyperplane pass through the origin, then we necessarily have b to be 0. You just need to substitute 0, 0, 0 into this equation and you get b must be 0. In this case, hyperplanes have special three properties. Let me list them. First property is clear. Origin contains in the hyperplane by definition. The second property is that if you have two points, or we can say two vectors, in the hyperplane, then sum of them is contained in the hyperplane. And third property, if you have a point in the hyperplane, if you multiply this point by lambda, basically if you scale all its coordinates by lambda, then the resultant point is also contained in the hyperplane. You can check these two properties basically just using this equation, that they are true. Now, we can use these three properties to define something new. This new thing is called linear subspace. By definition, a linear subspace of an n-dimensional space is a subset, V, such that three properties are satisfied. First of them, origin is contained in V. Origin here is just a zero vector. Second property, that if you have two vectors in V, then the sum is again in V. Sum of two vectors of the linear subspace must be contained in this linear subspace. And the final third property, if you have a vector in the linear subspace V, if you multiply it by some number, then the resultant vector is also contained in V. Just three properties. Here's example, absolutely standard examples of linear subspaces of n-dimensional space. First of all, it's a very important example, zero vector form a linear subspace. Sometimes people call it trivial linear subspace. You can check that all these three properties are true in this case, because there's only one vector in this vector subspace. Line through the origin in, for example, three-dimensional space. It's another example of linear subspace. A hyperplane then contains the origin also a linear subspace. We actually used properties of a hyperplane that pass through the origin to define linear subspace. And finally, the whole vector space Rn, the whole n-dimensional space, it's a linear subspace because the three properties clearly satisfy. Okay, one can check, we will check this later, that if we have two-dimensional or three-dimensional space, that these are only examples of linear subspaces of Rn. Also, sometimes linear subspaces in this course will be called vector subspaces. Now, here's a new example how one can construct linear subspaces using matrices. You take a matrix, M times N, real matrix. It has M rows, N columns, and we can define its kernel. By definition, its kernel, it's all vectors in n-dimensional space, such that if you multiply your matrix by this vector, you get 0. Let me remind you from the previous lecture that if you have an M times N matrix, And if you have a vector in n-dimensional space, you can multiply your matrix A by this vector to get a vector in m-dimensional space. Okay, sometimes kernel of a matrix is also called a null space. It's quite common actually. And this is a lemma which has to be checked by you. It is proved accurately in the lecture notes and in the book that the kernel of a matrix is a linear subspace of an n-dimensional space. This is very useful because quite often you can actually use this lemma to prove that some set is a linear subspace. Here's an example. Suppose we have this nice 2×3 matrix, and what is its kernel? Its kernel consists of all vectors in R3, x1, x2, x3, such that if you multiply matrix A by this vector, you get 0. But what does it mean? If you multiply A by this vector, you're going to get vector in two-dimensional space. Its first entry is x1 minus 2x2 plus 3x3. So, by definition, it must be 0. Its second entry is minus 4x1 plus 5x2 minus 6x3. So, by definition, it has to be 0 as well. So, kernel of this matrix is just this subset of R3 defined in this way. Okay, now we're going to define new term, which we actually already used during the last lecture, which is called linear combinations. If you have m vectors in n-dimensional space, and you have another vector, let's call it y, we say that y is a linear combination of vectors v1, vm, if y can be represented as a sum of these vectors, with coefficients lambda 1, lambda 2, lambda n. So basically, if you multiply first vector by lambda 1, second vector by lambda 2, the last vector by lambda m, if you add them, if y is this vector, we say that y is a linear combination of vectors v1, vm. It's very useful terminology. Here's an example. And if you looked already in some tutorial problems, you can see that there are some problems which uses linear combinations. Okay. Let now V be a linear subspace that contains these vectors. Then by definition, almost by definition, this linear subspace contains all linear combinations of vectors v1, v2, vm. To be precise, you have to use second and the third properties in our definition of linear subspace, plus maybe some induction. First, you take sum of two vectors, linear combination of two vectors, then linear combination of this vector and the third one, and so on. And then you can prove that such sums always contains in V, basically because the sum of two, these two vectors contains in V, and then you add third, and so on. It's better to check by yourself, but this is very useful properties. So again, you just can use it as a slogan. If linear subspace contains any number of vectors, then all of the linear combinations are also contained in our linear subspace. This is very handy and very useful observation, or maybe remark, that zero vector is a linear combination of any vectors. Look, if in this black box, if y is 0, you can put lambda 1, lambda 2, lambda m to be 0, regardless of what are vectors v1, vm, and you always get equality. So zero vectors always linear combinations of any given vectors. And now we are ready to give the first, in my opinion, important notation or terminology of this lecture, it's linear span. If you have m vectors in n-dimensional space, let it be v1, v2, vm, by definition, the linear span is a set of all possible linear combinations of these vectors. So basically, x contained in a linear span of v1, vm, if x is a linear combination of v1, vm. And we use this a little bit bulky notation for the span of vectors v1, vm. Sometimes you may omit curly brackets, but I usually use them. Yeah, and first important observation or remark or lemma, its proof is in the lecture notes or in the book, that the span of given vectors is a linear subspace of this n-dimensional space. So if you take any n, if you take n-dimensional space, Rn, if you take fix some vectors v1, vm in this space, then the span is a vector subspace. This gives you the very nice way how to generate vector subspaces out of finitely many vectors. Again, here is a crucial point that you have finitely many vectors, yeah, but they span as a vector space or linear space, linear subspace, which is usually contains infinitely many vectors. And here's an example. Suppose you have this 4 vectors, 5, 9, 2, 1, 3, 1, minus 2, 4, 3, 1, minus 3, 2. And all the possible linear combinations looks like this. And one can check that all of them contained in the plane in R3 given by this equation, x1 minus x2 plus 2x3 equal to 0. Why? Because actually each of these vectors is contained in this plane. This plane passes through the origin, so it is a linear subspace. And the linear combination of these vectors must be contained in this linear subspace, because we mentioned this in the previous slide. Okay, and now we're ready to define what is called spanning sets. If you have m vectors in Rn, and you take the span is a vector subspace in Rn, we say that these vectors span V. Basically, it sounds like tautology, but it's very handy. With basically vectors span, they span. So, and in this case, we say that this set of vectors is a spanning set for this vector space. So in this definition, spanning set is basically span V, but in some problems, you actually have to check it. So if you're given a vector space, if you're given a linear subspace with some fixed subset of vectors in it, sometimes you're going to be asked to check that these vectors span this vector subspace. Here's an example. We fix a plane in R3. It's a hyperplane in R3, but hyperplanes in three-dimensional space we usually just call planes. And we are given 2 vectors. First, we observe that these 2 vectors are contained in this plane. And the second, which has to be checked, which is not obvious, that these vectors span this plane. So what does it mean? It means that every vector in this plane is a linear combination of these 2. This has to be checked. We're not going to do this, but this is a nice exercise. And now, another very standard examples of spanning sets are called standard vectors in n-dimensional space. Usually in this course, they're going to be denoted by E1, E2 up to En. These are vectors with coordinates 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on. So basically, vector E1, it's a vector whose first coordinate is 1, and the remaining coordinates are 0. Vector E2 is a vector whose first entry is 0, second entry is 1, and the remaining entries are 0, and so on. So En is a vector whose all entries except the last one are zeros. This is called standard vectors in array. Basically, by definition, almost by definition, these vectors span n-dimensional space, because every given vector with coordinates x1, x2 up to xn is a linear combination of these vectors with coefficients x1, x2 up to xn. Please check this. And finally, let me list another lemma from the lecture notes. I didn't put it as a lemma here, just for simplicity. So if we have some vectors w1, wk, you take its span, and then you take some vectors v1, vm in this span. Then span of these vectors v1, vm is contained in the span of the vectors w1, wk. Basically, why? Because if you think about this, we already know that this set is a linear subspace. We mentioned this one slide ago. And also we mentioned that if you have some vectors in a given linear subspace, then the linear combination is contained in this vector space. But this set consists of all possible linear combinations of these vectors. So each of this linear combination contains here, so this subset is contained here. This is actually looks quite simple, but this is actually quite handy in some applications. Okay, and now let me mention another construction of some linear subspaces, which can be done using matrices. As before, we fix m times n matrix. M is the number of rows and number of columns. Then, by definition, its columns are vectors in m-dimensional space. And then we can take all possible linear combinations of columns, and we call it a column space. So again, by definition, column space of a matrix, it's a vector subspace of our m-dimensional space that consists of all possible linear combinations of columns of this matrix. And if we use some nice important remark, which I made in the last lecture, this space can be described like this. You take all vectors in Rm such that Y can be obtained as a product of A and a vector, some vector in Rn. Observations which I made during the last lecture is that if you take a vector in n-dimensional space, if you multiply your matrix A by this vector, then this is a linear combination of columns of matrix A with coefficients x1, x2 up to xn, with coordinates of these vectors, vector x. So again, when you take this product, you get linear combination of columns of matrix A, and vice versa. If you have linear combination of columns of matrix A, it can be written as A times x, where vector x is vector consistent of your coefficients of your linear combination. Okay, so this is the column space. And as kernel, column space is a vector subspace. So let me give you this example. You take matrix A, 2 by 3 matrix A, and then by definition, the column space is a span of these 3 vectors. The first column of matrix A is the second column of matrix A, and the third column of matrix A. One can check, this is not hard, that in this case, column space is a whole 2-dimensional space. You get all vectors in the plane if you take all linear combinations of those vectors. Yes. Absolutely in the same way, we can define row space. But remember that we decided that all vectors in this course are going to be considered as columns here. So since rows are not columns, in order to make them looks like columns, first we transpose them. So by definition, the row space of a matrix is a span of the transposes of its rows. So basically, you can think of them as rows, but let's consider all vectors as columns. So you take all the rows of the matrix, you transpose them, basically you rotate them by pi over 2, you got columns of transposed matrix, and then you take its span of these vectors. So for example, in this case, the row space is going to be space spanned by this vector. If you take its, if you put it as a column, like 1, -1, 0, and this vector, if you put it as a column 0, 1, -1. Again, by the properties of spans, column space and the row space are vector subspaces. But note that they live in different spaces. Column space, for example, in this example, is a subspace of two-dimensional space. And the row space is a subspace of three-dimensional space. Yeah. Okay, all of these three spaces we define today, column space, row space, and the kernel of a matrix, they all play very important role in this course. And you have to learn how to compute them in some cases and how to play with them. Okay, let me stop the recording.